this note I'll send you by email tomorrow, okay? Or maybe this evening itself. I'll send it.
Okay, no problem.
So,
Should I recapitulate some of the old lectures, or I go directly to today's lecture? What is the feeling? Do you remember? I mean, at least what are the topics that I have covered?
Participants, you should respond Professor Alam queries.
So what I am asking whether I should recapitulate what I did earlier, or I directly go to today's presentation.
I think you may briefly just tell that this has been
Okay.
done earlier.
Okay.
Yeah.
Okay. Okay.
from
So
the
Yes, that
last
will be better.
expression.
okay.
Yeah, yeah.
Okay. So
Yeah.
I think you have all got my note earlier. So just very quickly, let me recapitulate a few things
Yeah.
which will probably help you. So let me know when to start. Okay.
Yeah. I think we should wait for a few more minutes or
Okay.
2 to 3
Sure.
minutes.
Sure. I have no problem because
Yeah.
yes, today is the first day, so maybe
Yeah. That's why I'm asking.
Okay, sir.
Sure. I have no problem.
Yeah. Okay.
But my screen is visible, right?
Yeah. No
Yeah,
problem.
Good.
fine.
Visible, clearly visible.
হ্যাঁ আসসালামাইকুম একটা মিটিং চলছে ওর আর কি হ্যাঁ হ্যাঁ আমার হ্যাঁ 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 ঠিক আছে আচ্ছা ঠিক আছে
So should I start recapitulating or you want to wait for some more time? I have no problem waiting, but you decide.
I think, sir.
Or some people are still coming up. Okay. I mean, it's up to you. Okay. You let me know.
Yeah. Okay, sir.
I have no problem. Tomorrow is also a holiday. So so your classes are still all classes are online, right?
Yeah, sir.
Mhm. Okay.
I think we should start now. I just figured on behalf of the Department of Shalia University, I welcome all the participants to this second page of this lecture series, and I also welcome the speaker, Professor Jane Alam, for giving his valuable time to extend this lecture series. And now I request Dr. Mukleswaram to say a few words just to regarding this second page of the lecture series. Dr. Mukleswaram, can you hear me?
I think he is muted.
I think he is not.
No, he's
Okay,
muted.
sir, I think you should start, sir. Okay, so you can start recapitulating from the last lecture at least.
Okay. Okay, so let me just very briefly, I welcome you all to this second phase. Actually, so far what I have done actually quantize the scalar field also only, but our real world is governed, I mean, mainly by electromagnetic interactions, the interactions due to gravity and strong force and weak interactions. Now, among these four interactions, all know that gravity cannot be quantized yet. So we have only three other interactions: electromagnetic, strong, and the weak interactions. Now, this electromagnetic interactions, which is control all the physics of atoms, molecules, the entire branch of solid state physics, and everything which you see around us in our daily life. So the purpose of this lecture series is to quantize the electromagnetic field and calculate a few diagrams to show how the cross section can be calculated by using quantum field theory. Quantum field theory, as you all know, as I've also said in my first page, that it is only microscopic theory which can describe the microscopic world very accurately. And so far there is no alternative to this. And basically the philosophy behind the quantum field theory is as follows. This diagram tells you everything. You have classical mechanics, you all are familiar with this. And when you see some kind of inadequacies with the classical mechanics, then you use the quantum mechanics by elevating the dynamical variables in the classical mechanics to operators and use the quantization relations. So dynamical variables, they become operators, and then you use some kind of quantization relations or computation relations to make a transition from classical to quantum mechanics. And you also know that in the continuum limit, the classical mechanics gives a theory called classical field theory. I gave you an example of this, motion of continuous string. So when you take the continuum limit, then you get classical field theory. And in this classical field theory, the famous well-known theory of all classical electrodynamics is classical field theory. Maxwell equations and all falls under the category of this classical field theory. So when you take a continuum limit of the classical mechanics, then you get classical field theory. So when classical field theory fails, right, then what you do, similar to classical mechanics, you dynamical variables which you have in the classical field theory, you promote them to operators and use some kind of quantization relations to make a transition from classical field theory to quantum field theory. This part we have already discussed, right? And this classical field theory, which I have discussed in very detail, was the theory for the scalars, right? And this classical field theory, when I said that there is some inadequacies of the classical field theory to describe certain phenomena, is that the famous example is the photoelectric effect. Photoelectric effect you cannot describe by this by solving the Maxwell equations. By using the classical solutions of the Maxwell equations, you cannot describe the photoelectric effect. What you need to introduce the concept of quantum, right? The concept of photon you need to introduce in this, right? And that was the work done by Albert Einstein in 1905, where he used the quantizations of the classical field theory like classical electrodynamics and described the photoelectric effect. Now, a classical field theory, whenever there is some inadequacies, you just have to promote those operators, the dynamical variables to operators, and use some kind of quantization relations, right? Now, we'll see that how that can be done, how we can quantize the Maxwell equations, that we'll see. But I'll start with today with the Dirac equations. You all remember that this, you just, if you have time, you just go through my notes, which is almost, I have provided you 100 pages, handwritten notes. You can go through that, and you can see that how, systematically I have derived the expressions for the Lagrangian for the classical Lagrangian for the scalar fields by using the simple arguments of Lagrange group. I have just derived these expressions for L, and then from there, once you know the Lagrangian density, what I did actually in this Lagrangian density, you have the dynamical variable phi, right? And if you know the Lagrangian, you can use the analogy with the classical mechanics and can calculate the conjugate momentum conjugate to the variable phi by taking the derivative of this L with respect to phi dot, as you do in classical mechanics by taking the derivative of the Lagrangian with respect to q dot, where q is the coordinate variables and q dot is its time derivative. So similarly, what you do, you from the Lagrangian, you just take the derivative of this L with respect to phi dot, where phi is the dynamical variables, like q is the dynamical variables in class of classical mechanics. So once you know the dynamical variable, this pi and phi, right? Phi is the dynamical variable, pi is another, its conjugate momentum variable. Like in classical, when you make a transition from classical mechanics to quantum mechanics, what you did, you just use a commutation relations of q commutator p is equal to I h bar. Similarly, here you can use the commutation relations of phi and pi equal to equal time commutation relations, which I have already described, that pi at variable t and x prime, and pi with argument t and x will be equal to I, h bar is 1. We are using the natural unit, is equal to delta x minus x prime, because x is a continuous variable. So you have to use the, you have to use this Dirac delta functions. Like this is the analogy. So, this is the quantization conditions for the scalar fields. That is what we have done, and in this we have shown you that this Klein-Gordon equations, if you take the Fourier transform, you can show that they are actually collections of infinite number of harmonic oscillators, and we know how to get the quantum mechanics of a single harmonic oscillators. Just here what you do, you quantize the infinite number of harmonic oscillators. But here what you have to do, you have to sum over infinite number of oscillators. And since the p, this omega p, which was like the spring constant, this, because p is a constant continuous variable, this you can have infinite number of harmonic oscillators with frequency going from corresponding to p equal to 0 to p equal to infinity, like omega p is equal to p square plus m square. So this sum then you can replace by the integrations like phi and pi. These things we have done, and we have quantized. And after the quantizations of the classical Lagrange scalar fields, we calculated the Hamiltonians, calculated the momentum, and we have shown you that if you quantize the Klein-Gordon equations, then you get particles as a quanta. But those particles, we have shown that they also, if you recollect, those are actually the bosons, because of the commutation relation satisfied by these annihilation and creation operators. These are the things which we have done. And then for the classical scalar fields, we have also taken some example and calculated the cross sections, and we have also described how to draw the Feynman diagrams given a Lagrangians. So what I will not waste much of time there. This is just briefly which we have done. I will directly go to the little bit of the Klein-Gordon equations. I will repeat, and then I will go to Dirac equations, because this repetition will be required to introduce the concept of the negative energy states and all that. Okay, so I am going directly today to the Klein-Gordon equations. Okay, just very briefly, I will tell you what I have done is this, but the purpose of this lecture will be to tell you how to draw the Feynman diagrams and calculate the cross sections for electromagnetic interactions for particles like electrons and positrons and photons. Okay, so this is the Klein-Gordon Lagrangian for the Klein-Gordon equations which I have derived earlier, and the corresponding action was d4x times this L. And if you remember that this we got the Euler-Lagrange equations by extremizing this action, and the Euler-Lagrange equation was the Klein-Gordon equation. So this was the Lagrangian for the classical field. Put it in the this Lagrangian in the Euler-Lagrange equation, and you get the Klein-Gordon equation. Right? This is for the real scalar field. The scalar field can be complex also. Then the Lagrangian is del mu phi star and minus m square phi star. But this phi is nothing but a combination of the two real field phi 1 and phi 2. Phi 1 minus I phi 2, and phi star would be obviously phi 1 will be phi 1 plus I phi 2, and phi star will be obviously phi 1 minus I phi 2. Where this phi 1 and phi 2 are the two real scalar field, they will satisfy this kind of equations. And the Lagrangian for the complex field is this. And we have also, if you remember, that we have derived the Noether's theorem. What Noether's theorem says is that suppose you make a change in the phi, or you can make the change in x also. Since I have described that in detail, I will just be very brief there. Suppose you change phi to phi plus delta phi, right? And because of that change, if the action remains invariant, then there must be a conserved quantity. So what we did, we have given a phase transformation of phi, right? Like phi goes to e to the I alpha phi, where alpha is just a constant, and demanded that this action will remain invariant under that change of phi. If you demand that, then you will get a conservation law. Conservation law means you will get a continuity kind of equation like del mu j mu equal to 0. This also I have derived. And this j mu was nothing but, if you see your old note, it will be I phi star del mu phi minus phi del mu phi star. So this is the current which will be conserved if the action remains invariant under the transformation of the field phi under global gauge transformation. Why I am saying global? Because when I say phi equal to e to the I, phi changes to e to the I alpha times phi prime rather is equal to e to the I alpha phi, and when alpha is not a function of t or x, time or coordinate x, when it is a constant, then you will see that the current will be conserved, and that current j mu is given by this expression I have derived. And this j mu you can write as a temporal component, time component rho, and then the space component j. This notation also I have introduced, where this rho will be just mu equal to 0 component. So this will be phi star del phi del t minus phi del phi star del t. So this is the probability density. Like if you wish, you can call this is, if you wish to call it a charge density, then this is the charge density, and j will be then the current density. Okay. Now this is what we have done. So please remember that the Lagrangian which we have derived, we have never used any quantum mechanics. Please recall that what I did, I have used the Lorentz transformation of the scalar field under the Lorentz group, and from there I have constructed the Lagrangian. There was no quantum mechanics there, right? Usually, now I am entering to today's lecture. Usually what it is done in most of the quantum mechanics book, almost all quantum mechanics, ordinary quantum mechanics book, is that they use a different kind of approach, where this 4 momentum p you can write at the temporal component, time component e at the 3 vector p. This is the contravariant vector p mu, and if you put the notation below this mu below, then we call it a covariant vector e, and this becomes minus p. You know this matrix, you can make this transformation by using the metric g mu nu, which I have already said. So this p mu, if you take the product, then it will be e square minus p square because of the minus sign. Now this e square minus p square is nothing but m square, right? Mass, rest mass of the particle. You also please recall that we are using natural unit. So e square equal to p square c square plus m square c4, which I get from this equation. Since c equal to 1, I get E square equal to P square plus M square. Now, ordinarily what we do is E and P, they are the variables. In quantum mechanics, what we do is this E, we elevate this E to the operator and call it I h bar ddt, and P is minus I h bar this gradient. If I put h bar equal to 1, then E square equal to P square plus M square. And if I put these operators, I get this equation. Del square I del square del T square minus I del square is equal to M. Now, if you do a little bit of manipulation, then this equation will become this, box operator, which is nothing but del square del T square minus gradient square del square. So then you get this equation, right? This is the equation which you get just simply if you replace this E and P by the quantum mechanical operator. So, I have got now the Klein-Gordon equation. This is the Klein-Gordon equation, which I have got earlier by using simply the transformation law of scalar field under Lorentz transformation. But here I have got the equations by using quantum mechanical prescriptions. So these equations, you will have the tendency to say that this equation is a quantum mechanical equation, right? Because you will say this equation is a quantum mechanical equations because I have used the quantum mechanical prescriptions of replacing the energy by the time derivative and the momentum by the space derivative. Now, so this is the equations which I have got in this particular fashion. Now, from this equation, let us now try to get the expression for probability density and the current density. And you all know that I can do that by multiplying this equation from left by I phi star and this equation by I phi. And then subtract, if you do the subtraction, you will get this particular expression, where if I call this within this bracket, if I call this expression as rho and this expression as minus of j, then del rho del t plus divergence of j is equal to 0. So this is the continuity equations, right? Where rho is I phi star del phi del t minus phi del phi star del t. Same expression which I got earlier by using, you see here, by using the Noether's theorem. Okay, I would always suggest that you use Noether's theorem. That is a very powerful theorem. I will have much more to discuss about that later. But the equation which you have got is rho, which you have got is this. Now, so this is the probability density, right? Now, the Klein-Gordon, suppose I want to solve the Klein-Gordon equations. The Klein-Gordon equation can have a solution phi e to the minus I e t plus I p dot x. So now you put this phi in this particular, differential equation, right? You put that phi. This is the time derivative which will operate on this e to the minus I e t, and then this is the phase derivative. Now, for historical reason, this when you have in the exponential e to the minus I e t, that solution is called positive energy solution. I will come to that later. And this is the convention first used by Heisenberg, and this is now followed by everybody. Okay, so this is the solution of phi which I put in the equation. Now with this, if I know the phi, I can of course calculate the phi star. Only this I will become, this minus I will become plus I. So once I know phi and phi star, I will be able to calculate this rho, right? This rho I can calculate. Once I put the expression of this expression and its corresponding complex conjugate in phi, in rho, I will get rho is equal to 2e n square. N is a constant which appears simply as a normalization constant of the solution phi. Now, please note that this rho which I get is proportional to the energy. Now, Einstein's energy momentum relation is E square equal to P square plus M square. So when I calculate E, I have two roots, plus minus root over P square plus M square. So energy has a negative value. So probability density will become negative if E is negative. Now probability density can never be negative, right? That's a problem. Probability density can never be negative, but here it is becoming negative. Now, if you put this interpretation in the same footing and Schrodinger equations, in Schrodinger equation you have the probability density rho is phi star phi. That was always positive definite. That was never negative. But here it is, rho will not be positive definite because when I put that solution phi in the expression for rho, I got something which is proportional to E. Now E can be either positive or negative. So probability density is no more a positive definite quantity. Now this is a problem. So this probability density you cannot interpret in the same footing as you did for the Schrodinger equations. In Schrodinger equation, you said that psi star psi is probability of finding the particle at point t and x and so on so, right? Now you cannot do that because probability density finding the particle at certain space-time point can never be negative, right? It can be either 0, it can take any value from 0 to 1. If you properly normalize it, it can never be negative. So if you interpret this as a probability density and as the outcome of a quantum mechanical equation, then you are in trouble because rho is not positive definite, right? Now there are several explanations to solve this problem. One was that, I'll come a little later also. One was that you multiply this rho by electric charge, right, and then call it a charge density. And since electric charge can be both positive and negative, right, so rho can be positive or negative, right? So that way you probably can bypass this particular problem. But the problem will be, what about the neutral particle? Then are you saying that Klein-Gordon equations will not describe a neutral particle? You cannot say that. So that problem remains, that probability density is negative. But please note that when I have derived these equations simply by using the properties, transformation properties of scalar under Lorentz group, I have never used any quantum mechanical operators, quantum mechanical prescriptions. So there, this rho, I can say it was not a probability density. But now you have a problem. If you take Klein-Gordon equation as a quantum mechanical equations, then rho is not positive definite. That is creating a problem, right? Now you may again say, okay, I have positive energy and negative energy states. What I can do, I neglect all the negative energy states, right? Suppose you ignore all the negative energy states. That also you cannot do because if you neglect the negative energy states, then you will lose the completeness relations, which is essential in quantum mechanics. That you will lose again. So you cannot ignore also the negative energy solutions. So you have a problem here. Probability density is negative, and I cannot solve this problem because even if I try to describe this as a charge density by multiplying it by a charge, it will fail for the neutral particle. And also I cannot ignore the negative energy solutions, because if I ignore the negative energy solutions, then I will lose the completeness relations. Okay, so that I cannot do that. Now, so that is a problem with the Klein-Gordon equations if I interpret this as a quantum mechanical equations. Now Dirac, how Dirac solved this negative energy negative probability density problem, that let us discuss. The relations which we know is root E equal to root over p square plus m square. Now suppose you take this equation, this is a positive energy solutions, right? Suppose I want to obtain a quantum mechanical equations by using this relation, by promoting this E as a operator, P as a operator. I have a problem again. When I will expand this in power series of p square by m square, I will have infinite number of terms in the power of p square by m square. Now, if I put p as a gradient as del, I mean the space derivative capital delta here, right? Space gradient, then I will have infinite number of space derivatives in this particular equations, but time derivative will be only in the first order, right? That will be equations which will also not be acceptable. But what we want actually, what Dirac actually wanted, he wanted equations which should have a first order derivative both in space and time. Now here the problem is the time derivative will be first order, but you will have all powers of the space derivative, right? But any relativistic theory, you know, the time and space has to be put in the same footing. So if energy is in the first order derivative, then this should also the space derivative should also appear in the first order. So what Dirac did, actually, he said this H, the Hamiltonian, is just simply alpha dot p plus beta m. So if you linearize like this, then this p is coming as a first power. So this will have a first order phase derivative. This will have a first order time derivative. You will at least have the time and the space under the same footing. But here, if you expand that, you will get infinite series, and you will have all powers of the space derivative and first power of the time derivative, which is actually not putting this time and space in the same footing. So this kind of linearizations will let us see whether it will work or not. So H is alpha dot p plus beta m, and this, you know very well that the alpha dot p, this vector product, I can write always as a sum alpha I pi, as I goes to 1 to 3, right? Now the motivation for the Dirac equations was that we want to get rid of the negative problem with the problem which we faced with the negative probability density. We want to get rid of that problem. So I write this H as this, and then alpha I pi plus beta m psi is equal to 0. Now, if I square this, if I take this square H, if I make this H square, right, then that will give me here p square equal to p square plus m square. So if I take a square, if I operate H on the left, right, on this equation twice, I should get back the Klein-Gordon equation. So right, because H square or E square will give me p square plus m square, and that was the relation which was used to derive the Klein-Gordon equation. So so this is the Dirac equations. Dirac proposed this equation. If I make this H is H square, similarly this also I'll put twice, alpha pi plus beta m, alpha j pj plus beta m. Note that I is a dummy variable, so here I put alpha pi and here I put alpha j pj, but there is a sum over j. I am using Einstein's convention that if there are repeated index, then it is implied that there is a sum over those indices. So now you just simply break this product, expand this product, you'll get this particular equation. Now you see here I have a 2 alpha I, right, pi. So there is a sum. So this is pi square, right, pi square. So this is pi square means it is px square plus py square plus px square plus pi square plus pz square. So that term was always there. So p square will be there. So this alpha I square should be equal to 1. This coefficient should be 1. And then there was no term, cross term pi pj in the energy formula. You see here, there will be no square equal to p square plus m square. There is no px py kind of product. So these coefficients alpha I, alpha j plus alpha j alpha I, this will be equal to 0. Similarly, there is no term which appears as m into mass into momentum. So this alpha I beta plus beta alpha I should also be 0. And this beta square must be 1 because my h square must be equal to p square plus m square. So beta square should be 1. Alpha, sorry, there is be alpha I square. Alpha I square will be equal to 1. And all other coefficients alpha I, alpha j plus alpha j alpha I, this should be equal to 0. Alpha I beta plus beta alpha I should also be 0. If I put those 0, then by squaring the Dirac operator, I get the Klein-Gordon equations. That is what I should get because I have derived that from the Einstein's energy momentum relations. Okay. Now these alpha i's cannot be ordinary number because alpha I alpha j is not equal to alpha j alpha I, right? There will be a negative sign because of this particular form of appearance. So this alpha I alpha j are not ordinary number. Similarly, beta is also not a ordinary number. So alphas and betas are not ordinary number because if they are ordinary number, then by squaring this, I will not get the Klein-Gordon equations. So they are matrices. Now the question is, what is the, so if the alpha, beta, they are matrices, if they are matrices, suppose this is n by n matrix, beta is also, must also be n by n matrix, then if these are matrices, then psi should be this is n by n, this beta is n by n, then psi should be n by 1 matrix, n by 1 column vector, right? So this psi should also be a multi-component vector. So what is introduced here is that since I have shown you that alpha and beta are not ordinary number, they are matrices, psi should also be a column vector. And let us now very briefly see, there are sophisticated derivations, I'll comment on that, but let us see what is the dimension of these matrices, right? So let us see, study some properties of this matrices. Alpha I beta I is equal to minus beta alpha I. From that relations I can always multiply that by a unit matrix here. And if you take the determinant on both the side, then you will see the determinant alpha I, determinant beta will be equal to minus 1 to the n, where I is a n by n matrix, unit matrix, minus 1 to the n, determinant alpha I, determinant beta, right? Now, since determinant alpha, determinant beta, they cannot be non-zero, then e to the minus 1 to the n must be equal to 1. That means n must be even. So, alpha beta, if they are n by n matrix, this n has to be even, right? That is quite clear from these derivations. If alpha is equal to n equal to even, then the lowest value of n can be equal to 2. Let us see whether it can be 2 or not. Now you see other relations, other properties you can get by using this relation alpha I beta equals minus beta I alpha I, because if I want to get the Klein-Gordon operator from the Dirac operator, that forced me to put alpha I beta plus beta alpha equal to 0, and from there you can show that beta inverse alpha I beta equal to minus alpha I, right? Now if you take the trace from both this on both the sides, trace of beta inverse alpha I beta equal to minus trace of alpha I. Now you can use the trace algebra, trace AB equal to trace BA. So then if you use trace of beta inverse alpha I into beta equal to, I can write equal to trace of beta into beta inverse alpha I. So beta inverse will go. I'll have trace of alpha equal to trace of trace alpha I. That will indicate that trace of alpha I should be 0. Similarly, in a similar fashion, you can show that trace of beta is also 0. So this alpha and beta, they are matrices. They should have even dimensions, and then also they should have trace equal to 0. Now these alphas and betas, they are independent matrices, right? And in case of if I consider these 2 by 2 matrices, then there are only 3 independent traceless matrices that are available. Those are Pauli's sigma matrices, right? But you need 4. Therefore, the n cannot be equal to 2. N equal to 2 is then ruled out. Then the next higher dimension, which is even, is 4. So these alphas should be 4 by 4 matrices. And this alpha and beta are 4 by 4 matrices, and there are 2 famous representations for these matrices. Alpha is 0, sigma. Sigma is the Pauli matrices. So this 0 is a null matrix, 2 by 2 null matrix. Sigma is a 2 by 2 matrix. Of course, it is a Pauli matrix, which is 2 by 2. And this beta is I0, 0 minus I. I is a unit matrix of dimension 2. And the sigma x are very well known Pauli matrices. This is called Dirac Pauli representations. There is another representation which is called Weil representations. There alpha is minus sigma 0 and 0 sigma, and beta is 0 I0. I is the unit matrix. This sigma are the Pauli matrices. And you will see in both the in books, both the representations are available. But when you work out any physical problem, please stick to one kind of representations. I'll later tell you how this, in certain cases, there's while representations are preferred, are preferable. I'll tell you that later. Okay. Now, we all know this alpha and beta then is known to me. They are either unit matrix or sigma Pauli sigma matrices. These are known. So all the quantities in the Dirac equations alpha and beta are known now. So now let me consider this Dirac equation, which is I del psi del t. This is coming from the energy E. Alpha dot, this is P minus I gradient is the P, and beta M was already there. So this is the equations. And then after certain manipulations, you can get this particular equation. what you can do, you can multiply this equation from the left by beta, so that you get I beta ddt plus I beta alpha minus beta square m equal to operating on psi is equal to 0. Now you define a matrix called gamma, which is like you define a 4 vector. Beta is like the temporal component, and beta alpha is the spatial component. And del mu is that I can write as time derivative, temporal component, and the gradient delta here. So if I use this notation, beta I can call gamma 0, and beta alpha I can gamma vector. So this is like beta 0, and this is del 0. Del t is the temporal component of the derivative, and then this is gamma I del I. So this is like a 4 vector product. I can combine them and write there as I gamma mu del mu minus m psi is equal to 0, because coefficients of m beta square is equal to 1 that we have shown earlier. And this I gamma mu del mu minus m psi is equal to 0. This is the famous Dirac equations, where this gamma mu is beta into alpha, and then which you can write as gamma 0, temporal component, and gamma. So gamma 0 is beta and gamma is beta alpha. Since I know alpha and beta, all those quantities, I know now my gamma matrices. Okay, I know the gamma matrices. Now, just a comment here, important comment here. You see here what I have done. I have used the Hamiltonian H as alpha dot t plus beta m, and in place of H, I have used the quantum mechanical prescriptions, and in place of P, I have used minus I and the gradient. So that is also quantum mechanical prescription I have used, and I got the equations, Dirac equations. But let me just tell you, there is a completely different way to derive these Dirac equations. Just it can be derived from the transformation properties of the spinors under the Lorentz group. Like I have obtained the Klein-Gordon equations by using the transformation properties of the scalar under Lorentz group. You just use the transformation properties of the spinors under Lorentz group, you'll get the Dirac equations. This derivation is quite bit length, I mean, I should not say it's a lengthy derivative, but what it needs is one needs the knowledge of the Lorentz group. And since I understand there are MSc students who probably has not gone through the Lorentz group, so I am not going through that derivative unless you want me to do it. Okay, so this is the Dirac equations, and sometimes this gamma mu del mu is written as del slash. So del slash is gamma mu del mu. So Dirac equation is very simple. I del slash minus m psi is equal to 0. This is the famous Dirac equation. Okay, and we'll see how this Dirac equation has solved the negative probability density problem. All this mathematical part we have to do, because when we will be calculating the Feynman diagrams, we should have the knowledge of all this. We should have the knowledge of handling the gamma matrices, how to calculate the trace of the gamma matrices and all that. So little bit of mathematics is required, and to form the sound basis for the quantum field theory. We are not yet in the quantum field theory actually. Okay, because we are discussing the Dirac equation now, and since I have already told you that the Dirac equation can be derived by using the transformation properties of spinor under the Lorentz transformation, then this kind of approach, then nowhere you will be using the quantum mechanical prescriptions of replacing the energy by the operator I del t, right? So this is very, but here I have used the quantum mechanical approach. Okay, quantum mechanical prescription rather I have used here. Okay. But if I get the equations in this particular approach, in that case I will not say this is a quantum mechanical equations. I can say that is the classical field equations for the spinors. Like Klein-Gordon equation, I say that this is a classical field equation for the scalar. Like Maxwell equations are the classical field equations for vector bosons. Okay, Maxwell equations we will discuss later. That is there are a lot of tricks there, which we'll discuss later. Now, all these gamma matrices, as I said, that they satisfy these properties. Gamma 0 square, gamma 0 is beta. The notation, the expression, you can square it and show that this is 1. Gamma I, which is beta into alpha I, you can show that if you square it, you will get -1. And then gamma mu, gamma nu, anti-commutator. When I put this curly bracket, this is anti-commutator. This anti-commutator is equal to 2g mu nu, where g mu nu is the metric tensor. I have discussed this in the first phase, which is 1 minus 1 minus 1. Okay. So this is the anti-commutation relations. One also described a quantity called gamma 5. These are the quantities. It may sound like here as a mathematical quantity, but it will help you in physics later when we will discuss the chiral symmetry. Then this it will be clear why this gamma 5 and all that I have introduced. So this gamma 5 is nothing but I gamma 0, gamma 1, gamma 2, gamma 3. You know all these gammas because gamma mu equal to gamma for mu equal to 0, 1, 2, 3, all you know. So you know gamma 5 also. If you take all those expression for gamma 0, gamma 1, gamma 2, gamma 3, you can see that this gamma 5 will be minus 1, 0, 0, 1, when again 1 is the unit matrix. And one can easily check that gamma 5 dagger will be gamma 5, gamma 5 square will be 1, and gamma 5 will always anti-commute with gamma mu. This will be required later. It may sound little, you know, clumsy for you now, but it will help you. Now let us see the conservation of current. Like we have derived the equations for the conservation of current for the Klein-Gordon equation. So this is the Dirac equation, right? Now in Klein-Gordon equation, what we have done? We have the Klein-Gordon equation, right, for phi, and we had another equation for the phi star. If you know the equation for phi, for the Klein-Gordon equation, you can get the equation for phi star by taking simply complex conjugate. Here you have the Dirac equation for psi, but remember this psi is a matrix, gamma mu is a matrix. So be careful now you taking the complex conjugate. Now what we have to do here, since they are matrices, we have to take the Hermitian conjugate of the Dirac equations. And you know, when I take the Hermitian conjugate of this matrices equations, this equation will be M, just simply psi dagger. But this you have two matrices, one is gamma mu, one is psi. So when you take the Hermitian conjugate, the order will change. Like A B dagger, the Hermitian conjugate of AB equal to Hermitian conjugate of B into Hermitian conjugate of A. So AB dagger is equal to B dagger A dagger. Similarly here, when I take gamma mu psi dagger, it will become psi dagger gamma mu dagger. Okay. So when I take the complex conjugate, this equation becomes this, and this equation I will of course become minus I. Now multiply this equation from the right by gamma 0. So from right I am multiplying this equation by gamma 0. This is the gamma 0. And define psi dagger gamma 0 at psi bar. Right? This I am just defining as psi bar. Right? Now here I have already mentioned to you that gamma 0 square is equal to 1. So here I introduce a 1, gamma 0 square, gamma 0, which is 1. So I have just introduced a 1, gamma mu dagger, and then you have a gamma 0 already there, right? Now, because this gamma 0 has come because I have multiplied from right by gamma 0. Now, this gamma 0, gamma mu dagger, gamma 0, you have the representation for all the gamma mu and gamma 0. You can multiply and show that this is nothing but gamma mu. So gamma 0, gamma mu dagger, gamma 0 is nothing but gamma mu, right? And psi dagger, gamma 0 is psi bar. Now, if I use that minus I del mu, this will become psi bar because this gamma 0 psi dagger is psi bar, and this whole thing is gamma mu minus m psi equal to 0. This will give you the equation I del mu psi plus gamma mu plus m psi bar equal to 0. This is the equation. So we have got the equation for psi bar and psi, rather psi dagger and psi in analogous to Klein-Gordon equations. Now what you do, you multiply this equation from right hand side by psi and B from left hand side by psi and add them. If you add them, what will happen? This m psi bar and m psi, this term will get cancelled, and you will get a nice equation del mu psi bar gamma mu psi equal to 0. Okay. So this is the continuity equation again. If I call this psi bar gamma mu psi as a j mu, the current, then del mu j mu equal to 0. This is again the continuity equation. So j mu is equal to rho, this density, and j vector, which is the 3 vector. Now this rho is nothing but the j0, the 0th component, temporal component of the j. And then if I put, how do I get the rho, j0 or rho? Just I put here this gamma mu equal to 0. So psi dagger gamma 0 psi, this is the temporal component or rho, and psi bar gamma psi is the vector component. Now the probability density rho is nothing but psi bar gamma 0 psi. Now psi bar I have said is by definition psi dagger into gamma 0. This gamma 0 is already there, so psi. Now this gamma 0 square is again 1. So rho, which is psi dagger psi, is, suppose psi is a 4 vector which is a column vector with 4 components, psi 1, psi 2, psi 3, psi 4. Then psi dagger will be psi 1 star, psi 2 star, psi 3 star, psi 4 star. If you take the product, rho will be equal to psi I mod square, where I runs from 1 to 4. And see, this is always a positive definite quantity. So probability density in the Dirac equation is always positive definite, which was not the case for the Klein-Gordon equations. So by linearizing the time derivative in the equations, we have obtained the rho, the probability density, which will be positive definite. So the problem which we faced with the Klein-Gordon equations of the negative probability density is solved here to completely, that the probability density is again positive. Note here, in the Dirac equations, the time derivative comes as a first derivative, and which is also true for the Schrodinger equations, right? The time derivative there is in the first order, and the space derivative in Schrodinger equation in the second order, in the non-relativistic Schrodinger equation. So, what we got actually, the probability density is positive. This is a very nice thing, that one of the problem is solved, the probability density, negative probability density problem is solved. And by doing that, by linearizing these equations, which we will see later, though the main purpose of the Dirac equation was to solve the negative probability density problem, but he got a bonus. The bonus was that the same equation will give you the description for spin half particles, which is built in there. We'll discuss it, how it is built in. So this has solved the negative probability density problem and gave us a bonus, which is we have got an equation which will describe the particle which has spin half. We'll see that later. This is a extremely powerful equation, which for this this Dirac equations. And but you see how simple it looks like. It looks like a I del slash minus m psi equal to 0, but it is remarkably successful in solving the negative probability density problem, and also, as I am repeatedly saying, it is giving us a bonus in the sense that the spin half is built in that equations. You don't have to put it by hand. We'll see that later. Okay. Now, let me just again make a comment here, which I will make probably later also, is that this current density J mu, which you have got J mu as psi bar gamma mu psi, this conservation equations you have got, right? Now, as I said, that this conservation equations you can get if your Lagrangian, again for the Dirac equations you can have a Lagrangian. And then if the Lagrangian is invariant under certain transformation, then there will be a conserved current. And we'll show later that way also you will get this conserved current. Okay. And conserved current. Okay. Now, so probability density problem is solved. Now the solution of the Dirac equations you can write as size up, some function of p. What is u? I don't know. E to the minus I p dot x. When I'm writing p dot x, it is a 4 vector product. It is actually et minus p dot x. Right. So this is actually the positive energy solution for the Dirac equation. So I am saying positive energy solution, again by convention it is coming as e to the minus IET. That is the convention, as I mentioned, used by Heisenberg. Okay. In exactly the same way, Dirac equation can have also a solution psi equal to Vp, right? In case of u, I have just put V, and due to the Ip dot x, right? Ip dot x plus p dot x. Here it was minus p dot x, right? Now, so here the energy is coming with a positive sign, e to the IET. So that is actually called the negative energy solutions, right? So you have both positive energy and negative energy solutions. See, in the Klein-Gordon equations, we have two problems. One is the probability density was not positive definite, it was negative. In certain situation, it could be negative, and you have negative energy solutions. Dirac solved the problem of the negative probability density, but the negative energy solution is still there, right? So you can have a negative energy solution. This equation will admit the negative energy solutions. Now, the question is, how can you solve this problem? Because, negative energy solutions you admit. Now, how can a free particle have a negative energy solutions, right? Now, what Dirac did, he actually does this problem, right? He sidestepped this problem by using the Pauli exclusion principle. What did he say? He said that suppose for momentum p equal to 0, what will be the energy values? It will be E square equal to P square plus M square. So for momentum equal to 0, you will have E2 values plus M or minus M. Okay, so plus M and minus M. These are the two values you will have if momentum equal to 0. And if momentum is non-zero, then in this side you will have, all the energy states. And then what Dirac says is that this negative energy solutions, minus M and this is the 0. So any solutions which is below this, right, minus M with negative energy solutions, all the states are filled up by electrons. If all the negative energy states are filled up by electrons, and since electrons has to obey the Pauli exclusion principle, no other electrons will be allowed to jump in the negative energy states because they are already all filled up. And all the energies are filled up in the negative, and all the negative energy states are filled up. So you have infinite number of negative energy states, let us say, and you have filled up all the energy states but infinite number of electrons. And that states, Dirac said, is nothing, that is the vacuum. So Dirac vacuum is not empty. It's not something which has nothing. It has infinite number of electrons in the Dirac sea because all the negative energy states he has filled up by electrons. Okay, but that way he has saved the situations that no positive energy electrons will be able to jump into the negative energy sea. But the problem there will be is that you have, the Hamiltonian, please note that the Hamiltonian which we have taken for the Dirac equations, please have a look there. Where is that this equation? Let me just tell you, that is very important. This equation A alpha dot P plus beta M. So this Hamiltonian which you have written is for a single particle, right? Now the solutions which you have got, which are both positive energy and negative energy solutions. Now to save your solution, you are saying I need infinite number of electrons, because unless you have infinite number of electrons, you cannot fill up all the negative energy states. So that's a contradiction, that you started with a single electron Hamiltonian, and to save your solution you need infinite number of electrons. That's a contradiction. You cannot have. Who gave you that infinite number of electrons? That is the question one will ask. So Dirac equations as such has also a problem then, right? Because you don't have an infinite number of electrons. Who will give you that infinite number of electrons? We'll come to this problem again when. So that means that Dirac equations again has some problem which I'll discuss also later. But suppose I derive the Dirac equations by using the transformation properties of a spinor under Lorentz group, then I will never use the quantum mechanical prescriptions. Then I will not call it a quantum mechanical equations. I will call it simply a classical field equations for spinor. Like Klein-Gordon equation is a field equation for scalar. Maxwell equation is a field equations, classical field equation for vector particles, right? So if I treat Dirac equations as a quantum mechanical equations, then I have a problem that I have a negative energy solutions, and to save the negative energy solutions, I need infinite number of electrons, right? So that's a big contradictions. So But if I don't treat it as a quantum mechanical equations, then I don't have that problem. And we'll see how this quantum field theory will solve that problem. We'll see that. Now you see, so suppose here is an example that suppose you have a electron here. Sorry, you have a negative energy electron in the negative energy C with energy minus E. If you supply enough energy, then what can happen? This electron can go and jump into a positive energy states. So there will be absence of electron here, and that you can represent as a hole, right? That you can, so there will be a hole appearing here and an electron appearing here, right? So what will happen? An electron will go to this, will be at the energy state E prime, and a hole equivalently a positron, I mean with a electron with positive charge with energy E will be created. So if you supply some energy, what will happen? You will get an electron and a positron, but the supplied energy should have a threshold that E plus E prime must be greater than 2m. Now, what happened? You know, once this was done, that concept of negative energy, hole or antiparticle was introduced by Dirac, Pauli and Weisskopf. They tried to solve the problem of negative probability density in Klein-Gordon equation by multiplying this J mu, the current, by electric charge E, as I mentioned earlier. So since electric charge E can be both positive and negative, so what you will be able to say is that the current probability, I will not call rho as a probability density, I will call it charge density. But then again I said what will happen to the neutral particle. So let us see how this negative energy solutions gave rise to the concept of the antiparticles. We'll have more detailed discussions, but let me give you some hint of that. This Feynman and Stackelberg, you know, they gave interpretations of the negative energy solutions. You know, this J mu, this 4 current J mu, we have derived this expression for J mu. You remember Klein-Gordon equation, we got this J mu, and this J mu was phi star del mu phi minus phi del mu phi star. So phi, if you take as e to the ip dot x, n into to the ip dot x, and put in that expression, you get J mu as 2n square E, the energy, and P. And remember that its temporal component was 2n square E, and we had a problem that E was negative, so we said the probability density in Klein-Gordon equation can be negative, and that was a problem, and which Dirac subsequently solved it. Now, suppose I multiply this current by E and call it a electric current, current for the electrons. So J mu will be minus E 2n square EP, right? This will be for the electron because electron has a negative charge. So I have multiplied this J mu by minus E and got this is as a current, right? Current for the electron. Now for the positron, suppose I want to calculate the current for the positron, I'll just simply multiply this by capital plus E. So J mu for positron will be E into 2n square E pi, EP, right? This will be simply that. Now you see, I can take this, I can take here a minus E for the positron. I am working for the positron. Please remember, this is very crucial. J mu is this 2n square EP. To get the current for the electron, I multiplied by minus E. To get the current for the positron, I multiplied this by plus E, right? Now this plus E, I am just manipulating. I take a minus sign here, and then to compensate that minus sign, I multiply both E and P by minus sign here, right? Now, what is happening here is then as if this, you see, this current and this current is same. So positive current, positron current and electron current is same, right? Only thing is as if the electron has an energy negative and momentum positive, right? So a negative energy electron, right, is appearing as a positron, right? That's a very nice description. So if somewhere a positron with positron emission with energy will be equivalent to the electron absorption with energy minus E. This is very crucial to understand this, that the positron, as if the positron here, I am calculating here positive current for the positron, right? And then this positron is equivalent to electron, because you see this E, this is minus E, but then I have to reverse the energy. So negative energy solutions or negative energy states will appear as antiparticles. Okay, this is a crucial conceptions which we'll be using later. Okay, now you see in pictorially what you can say, that positron emission will be equivalent to electron absorption. You can see it in another way. You see, suppose I have a, what I said that the solution for the positive energy state is e to the minus IET. So minus IET. What I can do, that E I can, positive energy solution, that E I can replace by minus E, and T I can replace by minus T. So it remains as a positive energy solution e to the IET. But when then the negative energy solution, you see the negative energy solutions or negative energy which is now going backward in time is equivalent to positive energy antiparticle going forward in time. You see, this minus E, this was minus IET. I have replaced that E by minus E, T by minus T, right? So now this negative energy, as if going minus T means backward in time. So negative energy going backward in time is equivalent to antiparticle or positive energy going forward in time, right? So these conceptions will be very important when we will draw the Feynman diagrams to show the arrow sign in the diagrams for incoming and outgoing electrons. This you please try to understand, and if you have any problem, I'll again repeat this. But this is very important, okay? Because you see, this part is very important to understand, that electron, a positron, an electron with negative energy states is like a positron. See, it's just like a positron. This is very crucial, and the negative energy which is going backward in time is equivalent to positive energy antiparticle going forward in time. Because of this manipulation, you just check, have a thought about it. Now, one other very elegant way, just this is also a very elegant way to, some little discussion let me have on the Dirac equations again. So what Dirac wanted, actually, he wanted that some linear combination of del mu. This, when I am saying del mu, it contains both space and time derivative. Mu equal to 0 is the time derivative, and mu equal to 1, 2, 3 is the space derivative. See, he wanted that when this some combination of del mu will operate on a state psi, I should get some constant times psi. That kind of equation he got, and ultimately that's what he got. Now, so linear combination means, suppose I consider the combination C mu del mu. If C mu is just a number, then you will have a problem with the Lorentz invariant. That C mu cannot be simply a number. What we have shown you, that C mu has to be a matrix gamma mu. So I gamma mu del mu minus m psi is equal to 0. And if you wish, from here also you can show those anti-commutation relations which I have already derived. In this equation, what you can do, you can just operate this particular operator I gamma mu del mu plus m from left, and then just manipulate it. You will get, by squaring it, you demand that I must get back the Klein-Gordon equations. You will see that you will get the anti-commutation relations gamma mu equal to 2g nu mu. That we will get. So this, the anti-commutation relations we have already derived, but this is another very elegant way of showing this. Now, the Dirac equations which we have obtained by using the quantum mechanical prescriptions, as I mentioned repeatedly, that the same Dirac equations can be derived by using the transformation of spinors under Lorentz group. Like we have derived the expressions for the Lagrangian density of the Klein-Gordon equations, Similarly, you can derive the Lagrangian density for the spinoids, which will be psi bar I gamma mu del mu minus m psi equal to 0. For this psi bar, I have defined already, it was psi dagger into gamma 0. So once you know this Dirac Lagrangian density for the Dirac equations, you can calculate the action, which is L d4x. Now, once you know this, you can again extremize this action and get the Euler-Lagrange equations, right? And this Euler-Lagrange equations, you will get del L del psi bar minus del mu del L del of del mu psi bar equal to 0. If you put that L here, you will get Dirac equations. Now, you have two variables psi and psi bar. You can write this Euler equation in psi bar, or you can write this Euler equation in psi. When you write this Euler equation in psi, you will see again you will get the Dirac equation, complex conjugate of the Dirac equations. This is the Dirac equations, and this is the, if you remember, which I just discussed, this is the adjoint of the Dirac equation, conjugate adjoint of the Dirac equations, del mu I del mu psi bar gamma mu plus m psi bar equal to 0. Now, so this is also a way to derive the Dirac equations through Lorentz group. That discussions I will do later if I have time. The main purpose of this particular set of lecture is to discuss the Dirac equations, the Maxwell equations, and get the quantum electrodynamics, calculate some diagrams, right, and show you how to draw the Feynman diagrams, and how one can use this theory to calculate the cross sections and compare with experiment. And second thing which I have in mind is that I'll also discuss path integral formalism of the field theory by using the, I'll show you how you can use the path integral formalism to get the same Feynman rules. That will be the last few lectures. Okay. So now the solution of the, now we have the Dirac equations, I gamma mu del mu minus m psi equal to 0. I have to get the solution. So as I said, psi, you can write u p to the I minus p dot x. So this, if you put this solution here, simply you will get gamma mu p mu. So if you operate del mu here, you will get simply del mu will take away this x mu, you will have a p mu here. Gamma mu p mu minus m operating on u will be equal to 0. Now, if the particle will be at rest, then what will happen? It will be gamma 0 p0 minus gamma dot p. But if p is 0, then will be only gamma 0 p0. Now p0 is the energy of the particle, and if the momentum is 0, then p0 will be simply m. So gamma 0 m minus m operating on up is equal to 0. So gamma 0 is simply, as you know, I am using the Weyl representation, which is 0 1 1 0. So if you put gamma 0 here, then what you get is the, just 1 minute. Well, so then if you put the gamma 0 is equal to this, you can solve this particular equation. Okay. Now gamma 0 equal to 1 0 0 minus 1, if you put if you use the Dirac representation, then what you get is very interesting. You get this particular equations for the UP 0 0 1 0. Now you see this u it will have 4 component, right? It is u1, suppose I call it u1 u2 u3 u4, and if you operate this matrix on u1 u2 u3 u4, if you operate that, but you remember this 0 is a 2 by 2 matrix, this 0 is a 2 by 2 matrix, this one is a unit matrix, 2 by 2 unit matrix. So it will be a 4 by 4 matrix. If you operate that 4 by 4 matrix on that u, which will be a column vector with 4 entities like u1 u2 u3. Now if you operate this on those 4 by 4 matrix on this column vector u, you will see out of those 4 component of u, only 2 will be independent, 2 will be non-zero, other 2 will be simply 0. This is a remarkable result. Why? I'll tell you, because when the electron is at rest, then an electron can have only 2 degrees of freedom. So this is remarkable in the sense that when the electron is at the rest, and I am using the drag equations, what is drag equation is doing is that out of 4 component, it is putting 2 component to 0. Just you have 2 non-zero component. That indicates that when an electron is at rest, it has 2 degrees of freedom, spin up or spin down. This is remarkable. So what the drag equation actually does, it operates on the spinors and projects out throughout the unphysical degrees of freedom, which is very nicely shown here. If you follow the algebra, is that this is a 4 by 4 matrix. This is a 4 column vector with 4 entities. Now, if you operate that, you will see out of those 4 U's, U1, U2, U3, U4, 2 will be 0, right? So drag operator projecting out the unphysical degrees of freedom. You have imposed 4 degrees of freedom, but it is rejecting 2 and keeping 2. That means drag operator projects out the unphysical degrees of freedom. Similarly, Klein-Gordon equations, the operator Klein-Gordon equations operates on the scalar field phi, and it will project out all the states which are not satisfying the on-shell condition. By on-shell condition, I mean a particle when it satisfies the Einstein relation like E square equal to P square plus M square, then I call that particle is the on-shell particle. E square equal to energy square equal to 3 momentum square plus M square. That particle is the on-shell particle. So Klein-Gordon equation, what it does, the differential operator which you have in the Klein-Gordon equations, it projects out all the degrees of freedom which are not on shell. And that is right, because you have got the the Klein-Gordon equation by using the on-shell condition, E square equal to P square plus M square. Similarly, if you consider the vector equations, let us say Procca equations, which is a equations for massive spin 1 particles, it will have 4 component A mu equal to 0, 1, 2, 3, 4 components. In the Procca equations, what will happen is that it will projects out or rejects the unphysical degrees of freedom, and you will have only 3, because for a spin 1 particle you will have 3 degrees of freedom, like 1. If your spin is 1, then it has 3 components, +1, 0, -1. That is what the drag equation is doing here wonderfully, that you have this U is a, as I said, this is a 4 by 4 matrix. So U has 4 entries, U1, U2, U3, U4. When you operate the drag operator on that, it is rejecting the unphysical degrees of freedom and keeping only 2, because if you have a particle is spin half, it will have 2 degrees of freedom, not 4, plus up and minus up. This physics is very, very interesting, and I think you should we should do it. So I think this is a time I can stop here today, and tomorrow I will solve the drag equations and go towards discuss some more problems with the drag equations and discuss some more symmetries and go towards the quantization of the drag equations. So tomorrow, if I can complete the quantization of the drag equations, next week I will take up the quantization of the Maxwell equations, right? And then we'll combine these two, form the quantum electrodynamics, and get the interactions for the electrodynamics, and construct the Feynman rules for the quantum field theory. So today I am stopping here just to keep some time for the questions and discussions. Okay. Hello.
Yes.
Yes, sir.
Yes. Yeah.
Let me know if you had any problem today, because after a long time I'm starting. So let me know. Very frankly.
No, I think, yeah, Dr. Khan, yes.
I'm asking the participants to say something on this.
Because what I discussed today is a lot of repetition. So let me, I was maybe a little fast or something, but let me know.
Participants, please respond if you face any kind
Hello?
of probably.
Yes, please.
Yes, this is Ritobrata Mukhopadhyay.
Hi,
No,
Rajat.
sir. Yes, sir. So, no, I did not feel a jump. It was quite smooth. And I had done quantum mechanics in my previous semester. So, I had already done the Dirac equation.
Okay, good,
So,
good.
so I knew a good deal of what was discussed today.
Okay, good, good, very good. So, have you also covered some, symmetries of these equations um, like parity, charge conjugations,
I had
time
read
reverse?
parity. I've read it on my own from Ashok Das.
Mhm.
Charge conjugation, maybe not, but we did these continuity equations. We derived the continuity equation from everything. We also proved that the probability density is positive for Dirac equation. We did that.
Okay,
The normal things that usually come in net,
okay,
in the quantum mechanics, those topics were discussed.
okay, okay,
Yes.
okay. Anybody, please? I kept some time for discussion, so please use this time. Hey, Rajkumar.
Hello. Sir.
Rajkumar, you have also covered a bit probably. So,
Yes, sir. Yes.
any problem?
No, there is no problem.
Okay. But those who have not read it, let me know from them also, because you can help me to improve.
Hello, sir. I am
Yes,
Asadullah.
yes, please, yeah.
Sir, I did not have all these things, Dirac equation on all these things in IIT Guwahati.
Mhm.
So I did not read earlier these things.
Okay,
I am observing first time and it seemed quite fast for me.
okay, good,
Yes, sir.
good. Acha, okay,
Yes,
so
sir.
I'll be a little slow. Fine, very good. Thank you.
Yes, sir.
Yeah.
Yes, sir.
So you want me something to be repeated?
Okay, sir. I will go through the note and yes, tomorrow I will ask some
So
questions.
please don't hesitate, okay?
Okay, okay, sir.
Tomorrow by morning I'll send you the notes, or maybe tonight itself, okay?
Okay, sir. And if I have some questions related to quantum mechanics, can I
Most
ask
welcome.
them also? Okay,
Sure,
sir.
sure.
Okay, sir.
Or you can
Thank
send
you, sir.
me an email also. If I have time constant, you can send me some email also, okay?
Okay, sir. Thank you, sir.
And there was some student who wanted me to discuss the path integral. So are they still there, or sorry? I mean, please let me know if you will be interested in path integral, because that is a different game, okay?
I wanted to know that if we just go with this method, like
Mhm.
canonical quantization,
Mhm.
so is it like path integral is necessary, or is it just a different way of looking at the same thing?
I would not say necessary, but some path integral is also a very elegant
Good.
approach,
Yes,
and
that is true.
it will be very helpful if you, in some point of time in your career, if you do thermal field theory, okay?
Okay, then
Uh,
we should do it.
that is, and other thing is that this is a very important question that you have raised. Suppose you did non-abelian gauge theory. See, the thing which we will be discussing is abelian gauge theory, QED.
Yes, QET. Yes.
Right now, suppose you want to discuss QCD,
Hmm.
and in QCD, is very complicated, and there is something called on physical degrees of freedom, which you need to incorporate in your theory, which are called Faddeev, Popov, Ghost.
Okay.
And as an example, suppose you want to understand those things, then path integral formalism will be very helpful.
Okay.
And canonical is very, it's not.
Gets
I mean, path
lengthy.
integral is most welcome there for Faddeev,
That is-
Popov, Ghost, and all that.
Okay, then we should definitely. I'm also interested in path integral approach. I mean,
Okay.
that is good.
Okay.
So I am also doing in this semester. I am doing in my university. I'm doing general relativity. So it is a compulsory.
Yeah. Ritubrata, you are from which university or institute?
I am from Institute of Advanced Research, Gandhinagar.
Okay.
Yes.
So you are doing PhD there?
No, I'm doing masters. This is my
Okay,
final
great.
I'm in my final semester of my master. So I have general relativity. I'm also working in a thesis in general relativity.
Okay.
But quantum field theory is what I always wanted to learn. Which
Yeah.
finally I have gotten the opportunity through these lectures. Because here in Gandhinagar, there is only one person who is working in quantum field theory. Professor Apan Bhattacharya in IIT Gandhinagar. He's working in ADS-CFT. Other than that, everybody is working in either plasma physics or astrophysics. So
No, but
mostly,
PRL there are a few like Hiranmoy
yes,
Mishra.
PRL is there. Yeah, PRL. Yeah, that is true.
Okay, but anyway, it will depend on you. If you all want, I will continue with path integral. No problem. Okay.
Yes, sir. Just you should do your
Okay,
way.
no problem. We will. Don't worry.
Yeah.
Any other comments? Asadullah, I am very thankful that you have remind me that I should put a brake on my speed. Good.
Yes, sir. Thank you, sir. Sir, I want to talk with Dr. Abdul Khan, sir.
Yes, yes.
Luckily,
Okay.
this is out of topic, sir. Actually,
Okay.
I studied in Alamin Mission Belpukur, and I
Oh,
think you used to go there, and I was extremely inspired by you. But
okay. Thank you.
then I just discovered maybe 1 year ago that you are professor in Alia University, and
Assistant
today I am
professor.
talking. Yes, sir. I am talking with you today. I am feeling very good.
It's great
Sir,
to hear.
I was inspired extremely by you, sir.
It's all your interest. Okay.
Yes, sir. Thank you, sir.
Welcome. So, if there is no question or comments, then we should stop here. And Professor Kalam, will you say something for this session?
At the beginning of this talk, actually, my connectivity has gone. That's why I don't say anything about that.
I
Yeah,
noticed
Your
that.
connectivity has gone. I see.
yeah, yeah. I actually extend say a heartful
Why?
thanks to Professor Jane Alam because during his very busy schedule, he is giving so much time to us for giving this lecture series, and it is the continuation of the first one. So I must giving a huge thanks from the departments also, as well as from the Alia University fraternity, and these type of lectures actually giving a huge input to the participants. That's why a number of requests is coming from the participants that these lectures should continue, and of course it's a very positive signal for us for continuing this type of lecture series. And I thank you again, Professor Janayadam. Thank you.
Thank you very much. Actually, this is I somehow, though we have some kind of commitment to our,
Yeah.
own institute and all that, but
Yeah.
in a broader sense, this is our duty to whatever capacity we can. We should help the next generations because that is the way we can serve.
Yeah.
We don't have any other quality to do. With this very limited quality, we can help the country by educating, by helping them to learn, and that's all. I always feel very lucky to be in physics because I mean I don't know much about beyond physics fraternity. Because I am always surrounded then by very intelligent people. Apart from the fact that we are, studying the same subject which Albert Einstein studied. So okay, so that's I mean, I always very happy because I interacting with intelligent people, and especially with young minds, are always very it helps me to remain energetic rather. Okay.
Of course. And
Okay.
and this one is the start.
Yeah, and
Starting actually. Yeah. In near future, of course, we'll do more series of lectures. And
apart from quantum field theory, other subject also we can discuss, like statistical mechanics, non-equivalent statistical mechanics, other things also we can discuss. Yeah, sure. Sure. Whenever I mean, it's a very good way for me to spend my time also. Otherwise, so this is very useful for me too, right?
Yeah.
And nothing can be more satisfying than interacting with the young people. So that's okay.
Of course.
We should take this opportunities. I will try to take this opportunity.
Sure. I will be always there. No problem. Okay.
So we have been our head of the department, Dr. Moglesur Rahman, is there. So Moglesur, you can say something.
I think.
Oh, I see. Okay. We have also from Dean of Coachbihar Panchanabana University, Professor Probir Kumar Haldar.
Oh, I know him. Yeah.
You know him.
Yes.
Yeah. Probir.
Thank you, sir.
Thank you. How are you?
Well, sir.
Okay, good.
Few of our students also attending these classes. Just we know today.
Okay, I see. Okay, good. I'm very happy, glad.
Yeah. I give him the link to this
Sure.
to invite his scholars actually. Yeah.
Okay, good. Somebody, is there anybody from Goa IIT? Somebody was asking for the link. Is there anybody from Goa IIT? IIT Goa? Okay, no, probably okay.
Sir, I am from IIT Guwahati, sir.
Oh, you are from IIT Guwahati?
Yes, sir.
Oh. No, not
Sir,
IIT Guwahati, IIT Goa, I am saying.
Okay, sir.
IIT Goa. Oh, I see. Okay. So somebody wanted the link. I sent him, but probably there is some problem.
Yeah.
Okay.
Yeah.
Thank you, sir. Thank you.
Okay. So see you tomorrow.
Yeah.
Thank you.
Good night.
See you
Good night to all of you.
Good night to all of you. See you tomorrow at 7:30 p.m.
Sure.
Yeah. Good night.
Good night.